Good morning, ladies and gentlemen, and this is your host Rajiv Kulkarni from Global Electronics Talk Show. Every Friday at 8:30 a.m., we bring you the best possible topic that is applicable to the electronics manufacturing globally. As we discussed about last week, semiconductor packaging. So we'll continue with that discussion today also. But before that, I would like to thank you all for watching this show and giving your valuable time to watch this show, or later on also you can watch it because it is available always on YouTube link. And Global Electronics platform is basically to talk about electronics manufacturing, the pros and cons that and the challenges that we face in the electronics manufacturing, whether it can be the market segment can be consumer electronics, semiconductors, microelectronics, or we can talk about aerospace, automotive, medical electronics. It doesn't matter. Electronics manufacturing is the key thing that we are addressing, and we bring the top professionals, top industrialists, or the experienced, knowledgeable people to this platform so that they can share their experience, they can guide, they can suggest, and they can give their valuable inputs for us so that we could learn from them. With that said, we had last week our esteemed guest, Mr. Nilesh Badwe, and who is himself is a engineering graduated from IIT, and then that is Indian Institute of Technology, and then he moved to US and he did his master's and he's a material science technologist, I would say, and he did work in a corporation like Intel Corporation in US. Then he moved back to India. Now he is serving as assistant professor in the material science and advanced semiconductor packaging segment in the Indian Institute of Technology in Kanpur. Welcome back, Nilesh. How are you this evening?
Hi Rajiv, thanks for the kind introduction. A small correction. I never actually got my master's degree. I directly got my PhD. So
okay.
I don't have a master's degree.
So the universities recognized the intelligence level was so extremely par than actually required. So they just jumped you through the masters, and they said that here is a PhD for you, and that is a great achievement. Yes, great, Nilesh. Thank you very much for that. And so yes, we did discuss about advanced semiconductor packaging and the semiconductor packaging on the ecosystems in India. How it is shaping up, how it is taking the baby steps, I would put it this way, in the Indian technology, the trend which is happening now. Yeah. And I think it is very, very interesting discussion, I would say, last week that we had. And I'm just addressing the audience here that you definitely have to go back and go through that interview as well, because it explains how much effort the Indian Institute of Technology Kanpur is putting in to support the Indian semiconductor advanced packaging system. So today we are continuing with the actual advanced semiconductor packaging topic that involves quite a bit of technical discussion as well. And Nilesh, we did talk about, I just want to brush it up, and if you could please, what is exactly the advanced packaging And then how does it differ from the traditional packaging?
So before we jump on to advanced packaging or how it differs from traditional packaging, I'll briefly again quickly explain what is semiconductor packaging for those who may not know, right? So
That is
semiconductor
great.
packaging, it involves all the technologies that are needed after an after a wafer is ready, after all the ICs are ready on a wafer that are manufactured in a fab, before it goes into a system or before your system is ready. So everything that happens in between is part of packaging, semiconductor packaging, microelectronics packaging. So that includes starting from uh, wafer dicing, or sometimes if you need to thin down a wafer, it includes back grinding process as well, where a full thickness about 750 780 micron thick wafer is thinned down by polishing to whatever target thickness, and then it is diced into single ICs. After that, that wafer, these single ICs, they are packaged. That means these ICs cannot directly go on a PCB. There has to be something in between which is called substrate. So these ICs are connected to a substrate, and then that substrate gets attached on a PCB during our regular electronics manufacturing or SMT or through whatever that process is, right? So whatever happens to this silicon chip or a silicon wafer between that fab and final system is all part of your electronics, microelectronics packaging or semiconductor packaging. Now, the traditional one that typically includes taking an IC, putting it on a lead frame, wire bonding all the connections, and then putting it inside a mold. And now your lead frame has leads. If it is leaded package, it has leads that can go on a PCB.
PCB.
Right? There have been even further advancements that have happened. Those are still part of traditional packaging, where what we talked about is wire bond. Then there is flip chip method, where your silicon IC, it is not attached to a lead frame, but there is a substrate, and it is called flip chip. The reason is your chip is flipped.
Flipped.
Right? Typically, your chip with the connections is facing up. In some of the old generation packages, still in last 20-25 years or so, industry has moved towards flip chip technology, especially for the packages where you need high performance, where you need very dense interconnect density, high interconnect density or dense interconnects, right? So the chip is flipped, where you can use the entire array under your chip that gets connected on a substrate. The substrate can be either, there are different types of substrates: thick film, thick substrates, thin substrates, ultra thin substrates. So thick substrates are typically ceramic based, thin substrates are organic based, and ultra thin are silicon based, and so on. So this IC is flipped. Now that IC is attached on the substrate, and entire the reason the substrate, it works as intermediary between your silicon chip and your PCB. So it is used to to draw all the interconnections, take all those fine interconnections on a silicon chip to your much much more coarse or larger pitch interconnection on a PCB. Along with that, substrate is also used to deliver power from your PCB to your chip. And then it also serves a very important aspect, which we'll talk in more detail later, that is related to thermal dissipation, heat dissipation, right? So
Sure.
all of this is part of traditional packaging. Now, what started happening was, we'll quickly go to Moore's law. I'm sure those who are working in semiconductors, electronics, I'm sure all of them have heard what a Moore's law is. I'll still quickly mention, right? So Moore's law is something that Gordon Moore, he was founder of Intel. What happened was, in 1965, he looked at some of the trends in last 4 or 5 years at that time, like from 1960s, early 60s. He saw that the number of transistors on a chip, they were doubling every 18 to 24 months. And This was one aspect. The other aspect was related to cost. That means the cost was also becoming half every 18 to 24 months. So he wrote a very famous paper that is called as Moore's law, where he predicted that every about couple of years or so, your number of transistors on an IC, they'll continue to double, and then your cost will continue to half.
Mm.
That was predicted in 1965.
Wow.
All the way until almost until now, it has held true. The entire industry has been driven by this Moore's law. So the number of ICs at that time, which was few thousands or even few hundreds, now it is in the range of 5 to 10 billion.
Yeah. Yeah.
So that has been achieved by shrinking your size of
Size.
the gate or the length scale, whatever, between your source and drain, right? Size of the gate has been continuously shrunk, and then industry also started coming up with more novel technologies. I'm not going to go into any of those details, but now that size has shrunk down all the way to few atom wide. Right, so that's something that's slowing down the Moore's law. You can't really push your length scales below few atoms. Means they're like few nanometers or even less than nanometer, those kind of length scales we are talking about, right?
Correct.
So currently they're in few nanometer length scales. You can't really. The challenge with that is, ideally you can still come up with technologies, but it doesn't remain economically viable.
Viable, yeah.
You can't have a product if you're not going to buy a laptop or computer if it's going to cost $10,000, $20,000, right? So
Yeah.
that becomes a challenge. So what recently, in last few years, the industry, all these major companies, all the industry is driving towards is advanced packaging. And
Mm.
what that means is, you can't create one large single chip with all these large number of transistors. And the biggest challenge, the economics of this is revolved around defects, right? A single defect. If you have very large IC, a single defect means that entire IC is gone.
Yeah.
Now, if you have large IC, that means on a single wafer, if one, if you can get only 100 ICs, if there are two defects, your yield is down to 98%, which is typically not considered very good. You need to go into these multiple nines, right? So so what industry has started looking at is, let's break down these large IC into smaller ICs,
Correct.
which have very specific purpose. So instead of putting the entire system on chip, right? That means your CPU will be there, your memory is there, your GPU, your communication, all the functionality on a one large chip. Instead of that, what industry decided was, let's go with, they call it chiplet based architecture. So let's go with smaller chips. And these smaller chips, now you can put all of these smaller chips inside a single package. If you have everything on one large chip, the communication is going to be very fast. Your performance will be very, very high. But then, as I mentioned earlier, it's not economically viable. So you still need very fast communication between all of these ICs. When you break this down into smaller chips, you still need very fast communication. So even if you put all of these ICs on a single substrate, that communication may not be as fast. So in order to improve that, the concept that came was advanced packaging. That means heterogeneous integration. What that meant was, your communication through organic packaging is not very fast generally. The reason is, organic packages which are made of polymers, you cannot have very fine features. It's just inherent polymer feature, because of polymers, right? You cannot have very fine features. So, but that particular aspect is easy to achieve for silicon. You can already put nanometer length scales on silicon, right? So it's much easier to put micron size interconnections on silicon. That technology is very old, very well developed, and industry knows how to work with silicon. So what started was, you put multiple of these ICs on a single silicon substrate, for example. There are different technologies that different companies started coming up with. Some of the companies put these silicon chips, which will facilitate this connection between two separate ICs inside organic package.
Okay.
Some of them started putting those on top of organic package. But that entire communication is happening through your piece of silicon. Which is passive component. It doesn't have any ICs, it's not active, it doesn't require any particular power. It just takes signal from one IC, takes it to the other. Now that is, so putting these multiple ICs on single piece of silicon, right? And then now that piece of silicon goes on your organic substrate, which can be attached on a PCB. So that is called 2.5D integration.
Okay.
2.5D integration. So you have one substrate that facilitates all this communication between multiple smaller ICs, and then that substrate goes on your organic substrate, which is then connected to your PCB.
Interesting.
It has its own challenges. The biggest challenge, as all those who are working in package design, right? They would know that a challenge with all of these is related to, first is going to be your managing mechanical stresses, because your silicon has coefficient of thermal expansion of 3.5 ppm per degree Celsius. Typical organic materials, polymers, are much higher, in the range of 150 degrees Celsius per ppm per Celsius. But then generally you add some glass fiber, you make composites by adding silica particles to bring it down all the way down to 15 to 20. But still it is much higher than silicon, right? So whenever there is any communication that is happening, right, as your current is passing through your interconnects, there is going to be I square R Joule heating. Once that heat is generated, your silicon is going to expand. It's going to expand very little. Your polymer is going to expand quite a lot. And then we studied probably especially in India, we study this in 11, 12, that once that happens, your system is going to warp. So there are all these warpage starts, then that generates stresses, that causes problem during SMT, or all sorts of things can happen. So you want to keep your temperature to minimum. You want to create these strong interconnects. All of all of these challenges are there. You have to take the heat out.
Okay, let's take a quick break here and we'll come back.
Yes.
Welcome back to Global Electronics Talk Show. This is your host, Rajiv Kulkarni, welcoming you. If you're just logged in, I just wanted to mention that today we are talking to Professor Nilesh Badwe, who is from India, and he is based in Indian Institute of Technology in Kanpur. And today we are talking about advanced semiconductor packaging, episode 2. Last week we had episode 1, and we are talking about episode 2 about advanced semiconductor packaging. And the first half of it, he explained it so nicely that, what's the difference between the traditional and advanced semiconductor packaging. Welcome back after this small break, Nilesh. So let's continue your talk.
Sure.
I just wanted to give you a break so that.
Thank you. Thank you very much. Thank you. So, I mean, that's we're talking about 2.5D, right? So putting multiple chips on a single piece of, let's say, substrate side by side is 2.5D. Now, even that was not sufficient for some of the advancements. So industries have started looking into something called 3D packaging. So what that means is now industry has started looking at, instead of putting these ICs side by side, stacking them on top of each other. So the communication, instead of through another substrate, it can directly happen up and down through these chips. That's going to increase all these challenges related to major challenges, your thermal management. How are you going to take all that heat that is getting generated inside of these ICs?
But that is a good news for the people who manufacture thermal interface materials.
Absolutely.
Yes.
Absolutely. So that's where the industry is currently at. And then there are other newer and newer technologies that are coming in terms of how we can eliminate, for example, solder, right? How we can create interconnection that is entirely made up out of copper. The reason is copper, of course, has much higher electrical conductivity than solder. At the same time, generally what happens is, as there is heat generation, as your current is passing through your solder, it can lead to either thermomechanical fatigue related failures or electromigration, your intermetallic compounds that form between your solder and copper that starts growing. It can lead to Kirkendall voiding. I'm not going to go into detail what that is. Those interested can Google it. But it can lead to all sorts of these problems, and that can lead to failure. So just pure copper, entire copper-based interconnection, that is currently being looked into very aggressively in academia and industry.
So when you say this, one question comes into my mind is, what are the drivers, of the advanced semiconductor packaging?
So drivers, as I said, the major driver is what I just explained, right? It's how we can squeeze more and more performance into a single chip, which is still economically viable. So we talked about Moore's law that was given by Gordon Moore. So recently, a few years ago, about 3-4 years ago, Professor Rao Tumala, I did mention him last time as well, right? Considered guru in packaging. He's emeritus professor in Georgia Tech, and he has been consultant to pretty much all the companies in the world, major companies. He came up with Moore's law for packaging, a packaging version of Moore's law. And what that tells is that instead of now transistors on an IC doubling every few years, instead of that, number of interconnects inside a package, that's what will double every few years. That means you can put more and more ICs inside a single package. That means you cannot really reduce the pitch any more than where you are at, right? At least inside in your transistor or the length scales. But you can reduce the pitch further. Currently, typically less than 10 micron is not easy. It's considered one of the challenges. Few companies have come up with technologies where they are making these in high volume manufacturing, but it's not easy. So reducing your pitch less than 10 micron, the pitch between your silicon, your IC and substrate, to less than 10 microns, it's not easy. So there are newer and newer technologies that are coming to achieve that. one of the technologies that is becoming very popular is called hybrid bonding, where what happens is you take a piece of silicon, you attach to another piece of silicon. And the reason it is called hybrid bonding is at room temperature means you have your interconnection, which is made of copper. You have your dielectric, which is generally your nitride or oxide or something. And then your dielectric to dielectric connection happens at room temperature. And now your copper is not protruding outside your surface of your silicon. Through CMP, chemical mechanical planarization, your copper is flush to your silicon. It has slight dishing. That means it is slightly inside your below your surface of silicon. And that slight means I'm talking about 1 to 2 nanometers. So, and then two pieces of silicon come together. Your dielectric to dielectric attachment that happens at room temperature. Then you heat the entire system where your copper expands from bottom top. It bridges that couple of nanometer gap in between, and then your copper atoms diffuse into each other to form a flush joint. So now you have two pieces of silicon which are sitting on top of each other, and then they have interconnection between each other.
Wow.
This is currently the most advanced technique that is being used for interconnection to achieve this sub 10 micron length or pitch for interconnection. So these are some of the newer and newer techniques that are currently continuously being developed. And there is a lot of research going on in how to achieve this copper to copper bonding at as low temperature as possible for in as little time as possible.
High speed, as low temperature as possible, but the maximum efficiency and throughput,
exactly.
and at a economically viable.
Exactly.
So it's very interesting because how the technology is improving day by day, or advancing, I would say, not improving, advancing day by day. And because of that, these high efficient or the chips being manufactured to to actually catch the speed of that technology, I would say, because in an automotive electronics itself, as we see, I think the other day, if I'm not mistaken, there are like 30 or 40 sensors at any given point of time. I mean, you can imagine the electronics engaged in the automotive, and the chips has to be so fast, as you rightly mentioned, the speed it has to catch. And also not forgetting the fact that it has to be very high density chips, because to have the multiple interconnect between the chips, layer to layer, it is definitely I think challenging. But I always wonder how it can be economically effective. But again, the OEMs, the brand manufacturers, they are able to spend the kind of cost or the amount is involved. So why not develop this? So yeah, it's very, very I think highly insight information that you are sharing. Anything else you want to add, Nilesh, on today's advanced?
Go on discussing topics related to very details of how the interconnections can be made, but
Yeah,
I think those can be we can keep those for some time
yes,
later.
yes, yes.
That
We will
itself can be
definitely.
one separate.
Yes, yes, yes. I mean, we have multiple things, topics coming out of this advanced semiconductor packaging for the audience that I want to mention here. As Mr. Nilesh mentioned, the interconnect solution itself is a different topic that comes under the PCB part of it, and also the chip design part of it. And then we can also talk about the thermal management of the controlling, how we can control the heat dissipation. I mean, sorry, how we can control the heat generation, and how we can apply or imply the heat dissipation part of it, where thermal interface materials come into play in the advanced semiconductor packaging. So, I mean, there are like multiple topics that we will be touching as we move forward in this global electronics platform. So, Nilesh, we are almost, yes, please go ahead.
So just one thing that I wanted to mention before we conclude, right? So
yes,
all this discussion is related to electronics
manufacturing.
Mentioned was related to electronic interconnections to squeeze more and more performance into single chip, right?
Correct. Yes.
Question is, there is also going to be some limit to that at some point. So what's the next step? That's going to be, so industry has already started looking into optical interconnects or photonics. So that's going to be after this, that's going to be the next big thing.
Wow.
That where you're, of course, all of your communication is happening at the speed of light.
Absolutely. I mean, it's
Much,
very
much, much faster than electrons can travel.
yeah,
So
yeah, much faster than the electronics, electrons which they travel, and that's a very good insight, and that's a very good input, I would say, Nilesh. And so, okay, anything else you want to share to the audience before we
I
end
think
the
we can
show?
conclude by mentioning that the pace at which industry is moving, and there is so much scope for innovation. I think this is a right field to be in for next 10, 20, 30 years. So I would urge everybody that, do consider that your semiconductors, packaging, electronics, this is going to be very hot field in next few years.
Absolutely. Rightly said. With that, audience, I thank you very much for watching. If you haven't watched, please do watch and please share the link, and also request your colleagues, your friends, your contacts to subscribe the link, because Global Electronics, we are bringing you every Friday it kind of a talk show with the industry experts, with the faculty experts on the electronics manufacturing. With that said, wherever you are on this earth, be safe and be good, and be humble to people. Thank you very much.